Okay, so this is the second booklet in the 2018 end of year electronics exam. So this is going to be assessing criterion 5. Okay, so the student has presented the following block diagram for a system to count the number of turns of a fan without adding weight or disturbing the motion of the fan. The display so we've got a sensor, we've got a counter, and then a display. And it shows the total number of revolutions only. What would we use in the sensor circuit? There's a few things we could have used here. So we could use a light sensor. So a light sensor. But we could also use something like a Hall effect, which if the fan was made of metal, could pick that up. Basically anything that would detect the presence of the blade there. Okay, because there's two blades, it's going to pick up on 2 counts per revolution, so that's why they're going to divide by the 2. What could we use to make the circuit divide the number of pulses by 2? Well, a toggle type flip-flop does that. Okay, so if you connect the toggle type flip-flop up to that and connect the output of the sensor, as long as it's been debounced and squared up, you can feed that into a clock signal of a toggle type flip-flop, and that would divide the number of, so it would give a 1 pulse for every 2 pulses from the sensor. Okay, so if we now we've got 4 blades on the fan instead of 2, we could add a 2-stage toggle flip-flop. So here it would require 4 pulses on the input to give 1 pulse on the output. Okay. Question 16. So we've got ourselves a synchronous counter. So remembering the synchronous counter, you can see the clock here is connected to, or this clock signal is connected to all of the clock inputs of our flip-flops. Okay, and so here's our input there. And here is the truth table for the JK flip-flop. Okay, so how many output states are possible? Well, we have 3 flip-flops. Each one is capable of 2 different states. So 2 to the power of 3, which is 8. So this is also known as the modulus. So the modulus of our counter. Which feature makes the circuit a synchronous counter? I will discuss that just a second ago. The clock signal is connected to each clock pin. Okay, explain the function of the AND gate in the counter circuit. So that's there. So this is looking at when Q0 is 1 and Q1 is 1, would make these 2 inputs here go logic high. So remember with the, if you look at this, if J and K, which is the connected to the output of this NAND gate, this AND gate rather, both of those are logic 1, that makes this toggle mode. So that switches flip-flop 2. So it puts flip-flop 2 into toggle mode. When its output is 1. And Without going through all of the logic sort of analysis to ensure that, in order for the synchronous counter to actually count properly, what we need to do is be able to control whether it toggles or not. And so this is only going to toggle when Q1 and Q0 are 1. So this is going to toggle when the output is something 1 1. Okay. Whoops. It does that. So i.e. when count is at x 1 1, x where it doesn't really matter, that could be a 0 or a 1. Okay, so let's complete the timing diagram for the counter. Looking at this, we're told, we're not told whether it's an up or a down counter. Okay, so I think the best way to start this sort of thing is to start at a particular state. So here we've actually already told what it is. It's 0, 0, 0. Okay. Okay, so when Q0 is 0 and Q1 is 0, so if Q0 is 0, that's connected to the J of Q1. So that's 0. And K is also connected to Q0, so both of those are 0. So flip-flop 1 is not going to change. Flip-flop 0 will change on the first pulse of the signal here, so the input is connected to that there. So this is going to change. Oh, firstly we need to check, is it a positive going edge? Yes, it is. You can see we've got a positive going edge from the truth diagram. So this one's going to change, but these others are not. That's not a positive going edge, so that's going to stay. Okay, and then this is going to toggle. Okay, so we can actually sort of, and this is going to stay. So this is actually enough information for us to completely finish off the diagram. If if Q0 changed but Q1 didn't, it's not going to change on the next positive going edge. Actually no, this one might change it. So now let's look at this one. So we've got Q0 being 1. That's going to make this toggle the next time it gets a positive going edge. And when this one toggles, that's going to make Q1 go logic 1. So this is going to change. Okay. That's at 0 now, so that's exactly what it was before, so it's not going to change now. Okay, now this is at 1, so it's going to change again. So we can sort of now just look at the pattern that we're forming. And we know with counters that the frequency of these is always going to sort of halve. So this is going to change every 2 cycles of the clock, this is going to change every 4 cycles of the clock, and this is going to change every 8 cycles of the clock. We can look at the logic on Q1 to work out what Q2 is going to do. So when Q1 is 0, then the output of that is going to be 0. Doesn't matter what Q0 is doing. So as long as this one's 0, that's going to be 0. This is not going to change. It's not going to toggle. So this is not going to toggle until both, both Q0 and Q1 are 1. Okay. Oh, oops, it's not there. There, that's the next one across. So both Q0 and Q1 are 1, so now it's going to tell it to change. Okay, now it won't change again until Q0 and Q1 are both 1, and we get the clock there. You can see now we've got this 8 pulse. So looking at this, we got 0 or 0, 0, 0. The next count is 0, 0, 1. So let's just write that down. And that went 0, 1, 0, and so on. And you can see that this is counting up. Okay, so 0 in binary to 1 in binary to 2 in binary. So that's counting up. Okay, RC timing circuit. Let's just not include that in this one. We have talked about RC timing. In fact, I'll go through this one now. Okay, so RC timing is the time constant is the resistor times the capacitor value. So the resistance in ohms times the capacitance in farads. There's a shorthand way of doing that. It's resistance in kilo ohms times the capacitance in microfarads will give you the time in milliseconds. Okay, so what have we got for our resistor value? Okay. We don't actually have the value, but this time constant is the time to reach 0.63 of the applied voltage. So we've got 10 volts here. So 0.63 happens in 3 seconds, 3 milliseconds. So TC is 3 milliseconds, and this is the time constant. So just reading it off the graph. Just reading it off the graph here, like that. And to fully charge the capacitor is going to be 5 times that. You can see it's getting to 15 milliseconds, so it's 15 milliseconds there. That's we're fully charged, so that's it there. And if we replace it by a resistor of twice the value, we're going to double this, so that's going to double this. So the time constant now will be double, and so now what we're going to do is see that this voltage takes 6 milliseconds to reach, and this one takes 30 milliseconds to reach, and everyone is going to be stretched out same sort of way. Okay. So the frequency of the wave is initially 33 Hertz. This is actually going to be a filters question, so let's leave that one off. We haven't covered that yet. Okay, question 18. This is a simple Zener diode regulator. You can see there's a symbol for a Zener diode there, and we can see the voltage, it's 12 volts. And we've also got a power rating, 400 milliwatts. And we've also got a 500 milliwatt 100 ohm resistor in series with it. So this voltage will try and produce 12 volts. So 12 volts DC. If the input voltage was found to be unstable with a 200 millivolt peak to peak ripple, so you can see there's a diagram there showing what that might look like, with a DC offset of 15 volts, so it's going to be around about the 15 volt mark. How will the system affect the ripple? So the point of the Zener diode is that as long as there's enough current flowing through it, the voltage across it will be pretty much constant, and so the ripple will be removed. And so what you're going to see is a little bit extra current at the peaks of the ripple, a little bit less current at the troughs of this ripple, but the voltage is going to, and most of that voltage drop will happen across this resistor here. Okay, so this 400 milliwatt, the significance of that is that's the power rating, which will be determined, or will determine the current that the Zener can conduct or safely conduct. If you exceed that 400 milliwatts, the Zener diode will likely overheat and fail. Okay, diagram on the right shows multi-stage power supply. So we've got 3 Zener diodes of 2 15 volts and a 9 volt. Attached to an unregulated DC source, so that would be up there, would be that unregulated DC source. And we've also got a ground connection here that's in between. Okay, the lowest output shown is negative 15 volts. There. So this is going to be 15 volts. Well, 0 volts is 15 volts above negative 15. This is going to be plus 15 volts. And this is going to be 9 volts above that. So it's plus 24 volts. Okay. And what the magnitude of the voltage, so the size of the voltage of the source B, was going to be the sum of all of these, at least. We still need some voltage across this resistor in order for the to get current flowing through the rest of the circuit. So 30 plus 9 is going to be 39 volts. So at least 39 volts. So 9 plus 15 plus 15 equals 39. So that's going to be the voltage across all the Zeners. We need some voltage across the resistor as well in order to make it work. Okay, question 19 is an op-amp question, so we're not going to do that. Okay, question 20 is another op-amp question, so we're not going to do that. Okay, we could probably do this part C. Let's have a look. No. So, need to know how the comparator works for that one. Yep, so that both of those are out. Another op-amp question, so that's that. I'm not going to do that. And that's it for that section there.